Hey guys, we're going to start off with this same handout that we had before. I want to show you what this looks like so that you can see it yet again. Remember this sheet. It was the relationship between a function and its first and second derivatives. And just like last time, in particular, we're extremely interested in that section right there. Because what we're going to be doing today is we are going to be trying to take this information and we're going to try to sketch the graph of the original function if we have the derivative, which is the opposite of what we did earlier in the year, which was when we took the original function and sketched the derivative. This time we're going backwards. So I want you to start off. If you find this sheet in your packets, derivatives are driving me crazy. It says to cut out the graphs below. There are 4 sets of graphs. Each one includes the function itself, f of x, its derivative, f prime of x, and its second derivative, f double prime of x, for the set. So what I want you to do is I want you to cut out all 12 graphs, and here's what it looks like. You're going to have a spot on each sheet for set 1, the f of x, the f prime of x, and the f double prime of x. And then a second set, same thing again. A third set, and a fourth set, okay? And it doesn't matter which set's what, just as long as they're correct matches. And here are the 12 graphs that you can pick from. I don't really know if you can cut them out because I believe that when the Copy Center made our stuff, they ended up putting it double-sided, so you probably can't cut them out, but you could at least write the numbers in there. So for example, if you think that function 1 is the original function and its first derivative is 4 and its second derivative is 7, then you would come up here to set 1 and write 1 is the original, 4 is its derivative, and 2 is its second derivative. Okay, so I want you to pause for a second. Oh, don't know what happened there. I want you to pause for a second and I want you to go through and I want you to take those graphs, and I want you to think of different strategies you could use to help yourself and see if you can take all 12 of those graphs and put it in where it would go. Okay, so go ahead and do that right now. Okay, now I don't want you to go to the next slide until you have tried to correctly label the graphs, but I want to take a look at what the answers are. But before we do, I want to slide down here to this and talk about some strategies that you could use. First of all, notice that all of these graphs are polynomial functions. So one strategy would be to sort the polynomial functions into groups based on their degree. Like the cubic is the derivative of the quartic, the quadratic is the derivative of the cubic, and the linear is the derivative of quadratic. So that would help you to know that the lower the degree, the farther down the totem pole it would be. Second, like that is basically what I said for number 2, recognize that the derivative of a quartic is cubic is quadratic, etc. Third thing, pay attention to each group in terms of its in behavior. Is it negative x cubed or positive x cubed, etc.? Because negative x cubed would be to start from the left like this and come down. And that would change its derivative than if it started down and came up. Okay, so you want to pay attention to that. And then, of course, use the chart of the relationship between a function and its first and second derivative to determine things like when the first derivative is positive, the original function's increasing. When the first derivative is negative, the original function's decreasing, and so on and so forth. So here's what you should have come up with. You should have determined that in one set, regardless if you put it in set 1, 2, 3, or 4, but there should be a set where the original function is 1, which you can see is a positive x cubed. Its derivative is number 7, which is positive x squared. And its derivative is 5, which is positive x to the first. You can also see things like graph number 1 does not have a local max or min. Therefore, its derivative does not cross the x-axis at all. And you can also see that number 1 is increasing on its entire domain, and therefore its derivative is always positive. You can see that graph number 7 has a local min around x equals 1, and that there's a 0 in its derivative at x equals 1. and that the first derivative is decreasing originally, which means its derivative is negative, and then increasing, making its derivative positive. So it meets all the different requirements if you go back and look at the chart that we talked about from the relationship between a graph and its first and second derivative. Here's a second set. 3 is the first original function, 12 is its first derivative, 10 is its second derivative. This to me looks like a negative x to the fourth. Its derivative is negative x cubed, and that derivative is negative x squared. And again, there could be coefficients in front of there, but those are just the parent function of it. Okay, and again, you can see like there's a local max right in there in the original function, and that's why that's a 0 right there. And then you can also see that there is no local max or min. It flattens out right there, so that's almost 0, and then comes back down. A third set, 8, 6, and 11, you can see that this is a positive x to the fourth. Its derivative is positive x cubed, which has a derivative of positive x squared. And again, you can look to see that there's a local maximum at these 3 values, and there are zeros in the derivative there. Oh, excuse me, right there. And you can also see that you are decreasing, so the derivative is negative, increasing, derivative positive, decreasing, derivative negative, increasing, derivative positive. Local max and min in number 6 right there and right there, which are zeros in the derivative. You are increasing to here, so it's going to be a positive derivative, decreasing to here, so the derivative would be negative, and then increasing again, so back to positive. And then the last set, 9, 4, and 2, this looks like negative x cubed of some kind, then negative x squared, and negative x to the first. Okay, and again, same thing, like max here, 0 here, whole thing's decreasing, so all of its derivatives negative, increasing, so derivatives positive, decreasing, so derivatives negative. It has to meet the requirements that we've learned in everything else from that chart, or it cannot be true. Okay, now that's just kind of something to get us going, because what we're going to do now is we are going to take a look at graphs of derivatives, and we're going to go into the reverse direction. And we're going to use the graph of the derivative in order to sketch the graph of the original function. Now, why would this be important? Because the derivative is the velocity. And you might want to know if you have the velocity of some type of, an object, and you want to go backwards and find its position, then you have to go from the derivative to the original function. Or you might have the acceleration, the second derivative, and you want to go backwards to velocity and then backwards to position. So it's really important. Now, in this particular case, I gave you the equation. That is not usually what will happen. You won't get an equation. You'll just get a picture and graph it. But I want to show you what we've got going here so that you can kind of get your feel for it. This is the blank sheet that you have in your packet. After it, I've given you the answers. So I'm going to kind of go through the answers on numbers 1 and 2. And then I'm going to have you try numbers 3 and 4 on your own, and then we'll go back and check them. Okay, so here was the graph that we had of f prime of x, which is the equation y equals 2x minus 1. It says show 3 examples of what the original function might have looked like. Now, there's a reason for that. Remember that the graph 2x minus 1, it could be vertically translated on the y-axis into multiple locations, and it would still have this derivative. Okay, so there's more than one possible answer, but they all have the same shape and the same key features. So let's take a look at what some of those key features are. Okay, we know that when the derivative is positive, the original function is increasing. So I can see that the derivative here is positive from here to here. So I need to make sure from about 0.5 on, my original function is increasing, which you can see in all 3 graphs it does. So there, and you can even see I wrote a little interval. So it's increasing from about 0.5 to infinity. When the derivative is negative, the function is decreasing. So I see the derivative is negative from here to here. So I said from about negative infinity to negative 0.5, I need to make sure my function is decreasing, which it looks like right there. I also know that there's a minimum in my derivative around x equals 0.5 because f prime of x equals 0, and there's a sign change from a negative value to a positive value. Which again, if you look at our little chart, when you go from negative, which means you're decreasing, to positive, which means you're increasing, it means you've hit a local min. Okay? So we also now need to take a look at concavity. Because the derivative is increasing, okay? Go back and look at this chart again. This is one of those things where you do not have to take the second derivative. You're going to look at these two things. If you happen to have a graph of the first derivative, anywhere the first derivative is increasing means the original function's concave up. Anywhere the derivative is decreasing means the original function's concave down. And anywhere the derivative has a max or min means there's a point of inflection in the original function. Okay, so coming back to this page then, because f of x is increasing, f prime of x, is increasing from negative infinity to infinity, that means the entire graph, f of x, is concave up. So putting all three of those things together, we know we need to put a local min at x equals 0.5, but look what I wrote over here. We don't know the exact y value of the min. So any of these graphs are correct along with infinite others. They all have to have a local min at around x is 0.5. They all have to be concave up entirely, decreasing from negative infinity to 0.5 and increasing from 0.5 to infinity. And notice they all have the same shape of a parabola, which makes sense because, think about this, a parabola is the original function and its derivative would be a line. And so that would make sense that that would work. Okay, let's try another one. Let's say here's another graph, f prime of x, which happens to be a parabola. Show once again 3 examples of what the original function f of x might look like. Okay, so when f prime of x is positive, that means f of x is increasing. So I can see that f prime of x is positive from here up. So I'm going to say positive from here up. So I'm going to say, and also from here up, so I'm going to say from negative infinity to about 1/2, it's positive. And then again from about 2 to infinity, it's positive. And when the derivative is negative, f of x is decreasing. So that's going to be all this region in here. So that's going to be from about x equals 0.5 to x equals 2. Okay. I also can see from this that I have zeros here and here at x equals 0.5 and x equals 2. Here I change from positive to negative. Positive means increasing, negative means decreasing. So that means there is a local max around x equals 0.5. And then f prime changes from negative to positive around x equals 2. So that means it stopped decreasing and started increasing. So there's a local min around x equals 2. Okay. In terms of concavity, remember that to find the concavity, you are looking for increase, decrease. So f prime of x is decreasing from x equals negative infinity to about x is 1. So that would mean that f of x is concave down there. And then the derivative is increasing from about x equals 1 to infinity. So that means f of x is concave up there. And because the concavity changes at about x equals 1, that means there's a point of inflection at x equals 1. So again, when we go to sketch this graph, we don't know the exact y values of those max and min, but we do know the shape. We have to have a local max at around x equals 0.5. We have to have a local min around x equals 2. We have to start off by increasing concave down, decreasing concave down, increasing, and right there actually is a point of inflection, turn to decreasing concave up on all 3 of those, and then increasing concave up. Okay, these are not the only 3 graphs that are correct. There are many more that are correct, but they all have that same shape and all of those same properties. They just have different y values of the max and min. Okay, this is the end of part 1. I'll come back in just a second with part 2.